Hi, welcome back to Maths with Armien. In this video on probability, I'm going to start off with a brief overview of basic probability concepts, and then in more detail, I will look at the addition rule, mutually exclusive and independent events, and show how you can use tree diagrams and Venn diagrams to calculate and do probability problems. Please don't forget to subscribe to my channel, Maths with Armien. Hope you will enjoy the video. There are 8 units in this video. First of all, we're going to give you an overview of basic probability concepts. Then we're going to look at the addition rule. Then we're going to look at mutually exclusive events. Next, followed by dependent and independent events. Then we're going to look at applications using contingency tables. And we're going to have applications using tree diagrams, applications using Venn diagrams with 3 events. And then finally, with all my videos, there's always a exercise worksheet. So let's start. In this unit, I'm going to do an overview of basic probability concepts. Throughout the video, wherever this icon appears, pause the video, try the example, and then start play again, and then you can compare your solution to the one I have provided. The basic probability concepts would be definitions of the concept of probability, sample space, events, and outcomes. Then we're going to have some probability rules, and then we're going to look at complementary events and the use of and, or. What is probability? It is the mathematics of chance that enable us to predict the likelihood or foretell the likelihood of certain occurrences or happenings, and indicates the relative frequency with which we expect an event to occur. Briefly stated, probability is the chance that an event will occur. And to calculate the probability, we will have the total number of favorable outcomes divided by the total number of possible outcomes. Now, next we're going to look at some probability rules. And the first rule here is that the probability of an event occurring is always a real number between 0 and 1. In other words, the probability will be a value somewhere between 0 and 1, with both the 0 and the 1 included. So, for example, a probability of 0 means that the event will never occur. And if I have a probability of 1, that means that the event will always or definitely will occur. And a probability of 0,5 means the event is expected to occur 50% of the times. Let's continue here. Probability value can be expressed as there's 3 ways we can express it. We can express it as a common fraction, or a decimal fraction, or a percentage. Please note, a probability should not and cannot be represented as a ratio, right? Only as a common fraction, only as a decimal, or as a percentage. Now, the greater the probability, the more likely the event is to occur. What does that mean? Let's illustrate that by means of an example. There is an 80% probability that it will be raining tomorrow. So it's very likely that it will rain. Conversely, we can state that the smaller the probability, the less likely the event is to occur. In an example, there is a 10% probability that there will be load shedding this week. So it's not likely that there will be load shedding. Now let's look at the second rule. The sum of probabilities of all outcomes must always be equal to 1. What does that mean? Let's take an example. Flipping a fair coin. What do we mean by fair? In other words, we mean it's unbiased. It's not a doctored coin there. So if I take a coin, I can flip it, and it can either go, as you can see, either heads or tails, right? So the probability of a head is only heads and tails, so it's 0,5 or 1 over 2. And the probability of a tail is 1 over 2, which is 0,5. And 0,5 plus 0,5, simple. 0,5 plus 0,5 is exactly 1. Right? That's what that rule explains there. Now let's consider the third rule. the probability of two events happening together or one event after another event. So the probability of A and B, which can also be denoted as A intersection B, that is the probability of the one event times the probability of the second event, right? And here, because we have the probability, the product of the two probabilities of the one event and the other event, we refer to this as the product rule. What is essential here is the term and that we use, A and B, which that and can also be denoted as intersection, right? So A and B would then be the probability of the one event times the probability of the second event. It's important to note here that events A and B have to be independent. We will talk more about independent events a bit later. Now, let's look at the example of flipping a fair coin twice. So there we have one coin, and then we're going to toss it the second time. Okay? So the chance of getting a head twice is if the probability of getting a head is 1 over 2 or 0,5, then the probability of getting a head and then thereafter another head, so the probability of head would be the probability of head times the probability of getting a head. And what's the probability of getting a head? 0,5. And so it's 0,5 times 0,5. And calculating that, we get 0,25. 0,25 being 25%. So the chances of getting a head twice is 25%. Now let's look at the definition of some of the terms we've actually used here. An experiment is the act of making an observation, right? So if you do something, you observe tossing a coin or flipping a die, rolling a die. For example, you flip a coin and you record whether the side is facing heads. So that is an experiment, right? You flip a coin and you keep a record of, is it landing heads up or whether it's heading tails up. An outcome. What is an outcome? One of the possible things that can occur as a result of an experiment. So if you look at the flipping of a coin, what could the outcome be? That's right. It can either land up heads or it can land face up tails. In other words, there are two possible outcomes in the coin tossing experiment. What do I understand by sample space? It is the entire set of possible outcomes, right? For example, in a single coin flipping experiment, so in other words, when we flip a coin, the sample space can be heads, tails, right? So that is the sample space. What do we mean by an event? Event is any subset of the sample space, right? For example, if we have heads facing up, so the event would be head facing up. We could also have the heads not facing up. It's important that we understand the difference between the concepts of event and outcome. An event is a subset of the sample space, right? For example, if we take the probability of getting a desired number, so the event there would be getting a number, for example, less than 3, right? So the event would be getting a number less than 3. The outcome relative to this, an outcome is the result of an event. So what would the result be of getting a number less than 3? So the results could be either getting a 1 or getting a 2. So those would be the outcomes there. Okay. Now let's consider the sample space if we toss a fair 6-sided die, right? So it's a die with 6 sides. There's the die there. You can see there are 6 sides. A 1, a 2, a 3, a 4, a 5, and a 6. And what will the sample space be? It can be a 1, and it can be a 2, a 3, a 4, a 5, and a 6. So that's my sample space. A 1, a 2, a 3, a 4, a 5, and a 6. You can also represent the sample space using a tree diagram. So let's consider the case where we flip a fair coin twice. So there's the coin. So if we flip it once, the first flip, it can either be heads or it can be tails, right? and the probability of getting a head is 1 over 2 or 0,5. Probability of getting a tail is also 0,5. Now for the second flip, so if I have heads, then the next could be that I can get heads again, or I can get a tail. And the same with the other one, it can be heads or tails, right? And the probability again of a heads is 0,5 and tail is 0,5. Let's list the outcomes. So after flipping it a coin twice, we can have, as you can see there, we can have, just follow the color, heads and heads there, and then we have heads and tail, and then we can have tails and heads, and then we can have tails and tails. So those are the 4 outcomes that you can have. Let's calculate the probability. The probability of a head is 0,5, right? So those are the outcomes there, and the probability of getting heads and heads is 0,5 times 0,5, and we calculate that should be 0,25. The same way we can calculate heads and tails. It's 0,5 times 0,5. Tails and heads, 0,5 times 0,5. Tails and tails, 0,5 times 0,5. And you can see the sum of that, that's exactly 1. Now we're going to consider an example where we're going to illustrate the events in sample space, and we're going to use a Venn diagram to do that. Let's take the example of tossing a fair 6-sided die, and there you can see a die tossing there. What is the sample space? 1, 2, 3, 4, 5, and 6, right? Then consider the event of getting an even number. So what would the outcomes be here? The outcomes would be, that's correct, a 2, a 4, and a 6. Those are the even numbers I can get tossing a fair die. And event number B is getting a prime number. What's a prime number? The prime numbers we can get here is 2, 3, and 5. But what do you notice about those outcomes of those 2 events? That's correct, we've got a common outcome of 2. So if we represent A with that circle, that magenta circle, and we represent the B with this aqua blue, so the common 2 would be where they overlap, and that's where the outcome 2 would fit in there. Then we can complete the rest of event A. You can put the outcomes there. That's still missing is 4 and 6, and the outcome there for B would be 3 and 5. But the sample space consisted of 6 there. So there's one more. That's correct. One more. That's the one that needs to go there. Now let's consider the probability of getting an A and B. What do we mean by A and B? That means the probability of getting an even number that's prime, right? So which of these even numbers are prime? That's correct. That's the common one. What color is that? That's the green color. That's the AND part. So this is the AND part of the 2 circles that I have there for my Venn diagram. And that represents the AND there. So there's only one outcome, so it's 1 over 6. That's only the 2, so that's 1 over 6. Now we also want to consider A or B. So with that, what does that mean? It is getting an even number or a prime number. So it can be there, it can be the even numbers, or it can be a prime number. So it's all of, that's correct, it's all of these numbers here. Outcome can be 4, a 6, a 2, a 3, or a 5. And how many are there? There are 5, so the probability there is 5 over 6. Now we want to look at the sample space of tossing 2 fair 6-sided dice. So there I've got the 2 dice, green one, and you see they're changing color. So let's just use these 2 dice here. So this one here, there are 6 possible outcomes that can match with the 6 outcomes there. So that sample space will be 6 times 6, and 6 times 6 is 36. So there's a total of 36 outcomes there. Let's illustrate that. It'll be much easier illustrating them, the actual ones there. So this is the first die and the second die, the first die and the second die, the first die and the second die. And so you can have a 1, 1, you can have a 1, 2, and you can go through all of them. There I've got a 5, 4, and there I've got a 4, 2. Okay. We can also represent it this way. Instead of dots, you can use actual numbers there. And I've color coded them. I'm using a white die and a green die. So there'll be the white and a white with a green and a white with a green and a white with a green. Okay. Now notice here that there I have a 2, 4. So it's a white 2 on the white and a 4 on the green. But 2, 4, there's also a 2 and a 4 somewhere else there. But they're not the same. Can you see? You see this 2 is for the white one and that 2 was for the green. So 2, 4 and 4, 2 is not the same. Now let's go back to my actual dies there. There's my sample space that I have. And this is the sample space we're going to use for toss. If we toss 2 fair 6-sided die. Now let's look at an example here where we want to toss 2 fair 6-sided dice, right? But we want to roll 2 fours. So what's the probability of getting 2 fours? There we have 2 dice being tossed, and we want to see what would be the outcome here should be 2 fours. Now let's just look at the sample space there. Where do you see 2 fours? That's the only place where there's 2 fours, right? So that's the sample space. The total number of outcomes is 36, and there's only one. What's our definition of probability? The number of favorable outcomes divided by the number of possible outcomes. The possible outcomes is a total of 36, and the favorable outcome in this case there is only one. So in other words, the probability of getting 2 fours would be that's the only outcome we have, and these are all the possible outcomes. Now if we numerize that, that's going to be 1 over 36. So the probability of rolling 2 fours would be 1 over 36. Now let's look at another example. In this case we want to get 2 even numbers, right? So I need to look at my sample space and I need to identify where I get 2 even numbers, right? You see the 2 even numbers? That's correct. So I want to find the probability of getting 2 evens. So let's look at the 2 evens. Where do you see the 2 evens? That's where I have 2 evens. That's a 2, 2 and a 2, 4 and a 2, 6 and a 4, 2. Those are all. And how many are there? If you count them, you see there's exactly 9. So that's 9 over 36. And we'd like to simplify that. And that's going to be 1 over 4. But we can leave it as 9 over 6 in the meantime. Let's again take toss 2 fair die, but we want to look at the probability of rolling at least 1 2. What do we mean by at least 1 2? In other words, there must be a 2, and there could be the other dice could also have a 2. So that's our sample space. So if we want the probability of at least 1 2, let's follow. Where do you see at least 1 2? That's correct. Those are the cases where I've got a 2. I even have a case where I have another 2. That's 2 2. Okay, those are all the 2's are here and all the other 2's are there. So how many are there all together? We count them, we see it's exactly 11. So the probability is 11 over the total number of outcomes is 36. Now let's look at the example where we want to have 2 even numbers and at least 1 2, right? So in other words, when we roll, we want to see 2 even numbers, but those 2 even numbers, at least one of them must be a 2. Okay, so let's look at our sample space. So let's do each one separately first. Getting 2 evens, let's see, there's our 2 evens, right? And you know there are 9 possibilities there. Then getting at least 1 2, those are the ones at least 1 2. Now we want to find the probability of getting 2 evens and at least 1 2. Now if we take the one times the other, then I'm going to get 9 over 36 times 11 over 36, which gives me 11 over 144. But this is not correct, because if I look at this here, if I'm taking the one with the other, there are some cases here that this is at least a 2, but there are no, we don't have 2 evens there. There's no, I don't have 2 evens there, nor there, nor there, nor there, nor there, and nor there. And here I've got 2 evens, but I don't have at least a 2. There are no 2's in there. So in other words, we actually have to, that is not correct. Okay, so we actually have to remove those ones that don't satisfy this requirement of 2 evens. And now if we count them, how many are there? That's correct. It's going to be 5. So the probability of getting 2 evens and at least 1 2 is 5 over 36. Okay. Now let's consider another rule here. The complement rule. The probability that an event does not occur. Right? So if you want to find the probability of an event that does not occur, it will be equal to 1 minus the probability that the event will occur. Right? So then we can express this here. So the probability of an event not occurring, we can write this probability of A prime, or you can even say probability of A's complement. There are different ways to write it. Sometimes you can even put a little probability of A bar, but generally we say probability of A prime. That means not A. And how do we do that? It's 1 minus the probability of A occurring, right? So if you know what the probability of A is, it's just 1 minus that probability, which will give you the probability of the complement. And this we refer to as the complement. There, the complement of A. Consider an example. We want to determine the probability of not getting 2 tails if 2 fair coins are flipped. So let's look at the sample space and the outcomes. So those are the 4 outcomes we can have. You can have heads heads, or heads tails, or tails heads, or tails tails. And these are the associated probabilities that we previously calculated as well. So if I want the probability of an event not occurring, it's 1 minus the probability of the event occurring. So let's take our specific example. Probability of not getting 2 tails is 1 minus the probability of getting 2 tails. So 1 minus, what's the probability of getting 2 tails? We see there, it's 0.25. So that's 0.25, and simple arithmetic, 0.75. We could also have just looked at the opposite there. Those are the cases where you are not getting 2 tails. So it's actually the probability of not getting 2 tails is the sum of probability of getting 2 heads, getting a head and a tail, or a tail and a head. And getting that sum, 0.25 plus 0.25 plus 0.25 is exactly also 0.75. Right? So you can either do it with 1 minus, or you can just find the sum of the other probabilities there. In this unit, I'm going to do the addition rule. Wherever this icon appears, pause the video, try the example, then you play back again, and then you can compare your solution to the one that I have provided. Here we're going to look at the union of events, and we're going to use the term or. Okay, so let's consider the probability of either of 2 events occurring. So one event or the other event occurring. And this here we're going to use the union of, so the or refers to the union of events. So when we have or, that's the union of events. So the probability of A or B, which we can also write as the probability of A union B. Okay, so we're going to look at that. Now let's look at the union of 2 events. I'm going to use an example to illustrate the probability of the union of 2 events, and then to be able to derive a formula to determine the probability of the union of 2 events. So in this example here, we have a class of 30 learners who have a choice of 2 subjects, mathematics and accounting. Right? So there we have the sample space, and we use a rectangle there. And then the event M is the event of taking mathematics. That's represented by that magenta circle. And the event A, taking accounting, that's represented with the aqua blue. Okay. Now there are 30 learners taking in the class, so that's where the 30 goes. That's the total number of learners in the class. And the number of learners who take mathematics is 20, so though that goes to the mathematics learners, and 15 take accounting, so let's place the 15 there. But what do we notice about the mathematics and accounting? If I find the sum, we see that it gives us a sum of 35, and which is a lot more than the class size of 30. So how do we explain this? That's correct. There are some learners who take mathematics as well as accounting. So in other words, there is an overlap. In other words, we have the 2 circles, they need to overlap. So in other words, there That's the situation that we have. And what is the overlap? The overlap is 5. 35 minus 30 gives me 5. So we can see there's 5 learners taking mathematics, and the same 5 learners also take accounting. You see there? There's the 2 colors, 5 taking mathematics in the background there, and 5. So we've got the same, so we have to remove one of those 5s. Right? Now we can calculate the remaining portion there. So that is, I've got 5, which is those who take mathematics as well as accounting. And then if I take the 20 from mathematics minus 5, that gives me the 15. And for accounting, 15 minus 5 will give me the 10. And now we can see 15 plus 5 plus 10, that gives me my 30. So that I've represented that properly in this Venn diagram. Let's look at the probability now. So we want the probability of taking mathematics or taking accounting. So the number taking probability for taking mathematics, we add that to the probability taking accounting. So that's 20 over 30, and there are 15 learners taking accounting, so it's 15 over 30. But we've got an overlap, right? So we need to remove that portion. So we remove what that's 5, so it's 5 over 30. And if we just balance this out, 20 plus 5 minus 5 gives me 30, and 30 over 30, that's correct. 30 over 30 is exactly 1. Okay. Now we can see, if we take the probability of the union of 2 events, then it's the probability of the one event plus the probability of the second event minus the probability of their intersection, right? So we state it this way: the probability of A or B is the probability of A plus the probability of B minus the probability of their intersection. Now let's just recap the addition rule. Union of 2 events, probability of A or B is A, probability of A plus the probability of B minus the probability of A and B, which we can also write, instead of or we can write the union symbol, and instead of the and we can write the intersection there. So it's the probability of the one event plus the probability of the other event minus the probability of their intersection. Now let's look at another example here. In this case we have 2 even numbers. We want to determine the probability of getting 2 even numbers, or at least 1, 2. Let's use our sample space for 2 6-sided dice. So there we have the sample space, and you can see we've got our 36 outcomes. Probability of getting 2 evens. Let's see where are the 2 evens. We'd added previously. That's the case where we have cases where we have 2 evens, and we see there's a total of 9. So the probability is 9 over 36. Next, at least 1, 2. Can you see where's at least 1, 2? We did it previously. So that's the cases where we have at least 1, 2. And if we do count that, we see there's exactly 11 where we can have at least 1, 2. Now we want to determine the probability of 2 evens or at least 1, 2. Okay. Now, if I take 9 over 16 plus 11 over 16 giving me 20 over 36, that is not correct. Because if we look at the sample space and the way I've done the shading, there are cases here where I've got a duplication. You see? There I've got, that appears twice because it appears with the green and with the magenta. That one is there, and that one there, that one there. So it's actually 5 duplications there. So that is not correct. Okay? So let's use our addition rule, and we'll do it properly. So there's our sample space, and we've highlighted. So probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Probability of A or B, right? So probability of A is the event where we have 2 evens, so that will be the 9 over 16. Probability of B is the second event, that's at least 1, 2, so that will be 11 over 36, right? But now because of the duplication, you see, I want to remove 2 evens and at least 1, 2. And if you look at that, that's what I want, that's the duplication I want to remove, and that is 5 over 36. If I do that little bit of arithmetic, 9 plus 11 subtract 5 is 15, and 15 over 36 I can easily simplify as 5 over 12, right? So that's the probability of getting two even numbers, or at least one, 2. In this unit, I'm going to look at mutually exclusive events. Wherever this icon appears, pause the video, try the example, and then start play again, and then you can compare your solution to the one that I have provided. Mutually exclusive events are events that do not have any outcomes in common, right? Let's look at the following. If you look at that, you see there's event A and event B, and they overlap, so they do have something in common. So when we say they're mutually exclusive, that is what they have. They should have nothing in common. Now, two events are mutually exclusive if and only if. See, there's two events. So the first one here, they cannot occur at the same time. So that's one of the main requirements of being mutually exclusive. Or they don't have any elements in common, right? You can see they have nothing in common there. They don't overlap. So the intersection of the two, you can see there's the intersection. The intersection is empty. There's no intersection. And the probability of A and B, right? A and B is 0. Then we can also now have that the number of elements A or B is the number of outcomes of the one event plus the number of outcomes of the other event. And the probability of A or B, if we take our addition rule, see there's our addition rule, because they are mutually exclusive, then this addition rule there, you don't have to subtract, that is 0. So in other words, the addition rule is now just probability of A or B is the probability of A plus the probability of B. There's no need to subtract because they have nothing in common there. Now let's look at the union of mutually exclusive events. In other words, we look at the addition rule here. So that is the addition rule. Probability of A or B is equal to probability of A plus probability of B minus the probability of their intersection. But because they're mutually exclusive, the probability of A and B is 0. So that is a 0. So in other words, the addition rule is now modified, and the addition rule is probability of A or B is the probability of A plus the probability of B. Now let's consider the example of flipping a single fair coin, right? So we have, there's our coin. So in other words, it can be flipped heads, and the other option is can be flipped tails. We know from previous there that the sample space is heads and tails there. So the event of getting a head is 0,5, and the event of getting a tail is also 0,5. Right? And you can see 0,5 plus 0,51, and you cannot get a head and a tail. Right? You cannot get a head and at the same time you get a tail, so there's no overlap. Probability of A and B occurring, that is 0. Probability of A and B occurring is 0. Therefore, A and B are mutually exclusive events. Now let's look at another example here. Here we're going to have the rolling of a single fair die. The sample space, we know the sample space would be 1, 2, 3, 4, 5, and 6. Consider the one event, getting an even number. So what would the outcomes be? A 2, a 4, or a 6. Event B, getting an odd prime number, the outcomes would be 3 and 5. Now what do you notice about that? 2, 4, and 6, and 3 and 5. That's right, they've got nothing in common. So that's how we represent them. So that's the 2, 4, and 6 for the A, and the 3 and 5. But because of the sample space, we must not forget the 1 that needs to be added there. So the probability of A is 3 over 6. It's 1 over 2. Probability of B is 2 over 6, which is 1 over 3. Okay. So we now notice here that the A intersection B, there's no intersection. So the probability of A and B is 0. So therefore we can see here that event A and event B are mutually exclusive events. Now let's look at the example of tossing two fair dice. There we have our sample space, consists of 36 outcomes. Let's consider the event A, where we have at least one 5. Can you see where we have at least one 5? That's correct. Those are the cases where we have at least one 5. And how many of them are there? 11. So the probability is 11 over 36. Next, we want the event of getting a sum of less than 4. Okay, if I look at the sum there, 1 plus 4 is 5. It's not there. You see where we have a sum of less than 4? Those are the 3 cases, right? In this case here, it's 2 plus 2, which is 4, which is not less than. So those are the only cases where I have less than 4. Now, if you look at that magenta and this green, they have nothing in common, right? So in other words, probability of A intersection B, there's nothing in common, so that's 0. Therefore, A and B are mutually exclusive events there. Now let's look at another example where we're going to apply the concepts of mutually exclusive events. Here we have two events A and B, and it's given that the probability of A is 0,6, probability of the second event is 0,3, and probability of A or B is 0,8. Are the events mutually exclusive? Okay. So we have to show, if we want to show them mutually exclusive, we have to show that probability of A and B would be 0. So let's use our addition rule. There's our addition rule there. Probability of A or B is probability of A plus the probability of B minus the probability of A and B, or the probability of their intersection. We are given the probability of, let's put that there. So we are given the probability of A or B. See, that is 0,8. Say there's a 0,8, and we can insert it there. Probability of A is given, that's 0,6, and we can substitute there. Probability of B is 0,3, and we can substitute it there. And so the only one that's missing is probability of A and B. Doing a little bit of manipulation, we transpose the probability of A and B on the left side, and then we have 0,6 plus 0,3 minus 0,8. I do the little bit of arithmetic there. That gives me 0,1, and we know 0,1 is definitely not 0. So therefore we can deduce, you see, 0,1 is not a 0. So the probability of A and B is not a 0. And because of that, we did not get the 0. We can then deduce that A and B are not mutually exclusive events. In this unit, I'm going to look at independent and dependent events. Wherever this icon appears, pause the video, try the example on your own, start play again, then you can compare your solution to the one that I have provided. Let's consider independent events first. What are independent events? Occurrence of one event not affecting the probability of the second or another event there. So the one event does not affect the probability of another event. We can also state it is that the outcome of the second event is not affected by the outcome of the first event, right? So the first event doesn't affect the second event's outcomes. So now we have a product rule for independent events. So the probability of A and B is equal to the probability of A times the probability of B. Okay, so the probability of event A and event B is equal to the probability of event A times the probability of event B. And that is the product rule for independent events. Now let's look at the union of independent events. Taking the addition rule, there's the addition rule, probability of A or B. the probability of A plus the probability of B minus the probability of the intersection of A and B. But because they're independent, the probability of A and B is actually the product of the probability of A and the probability of B, so that can be replaced, probability of A times B. So in other words, for the union of independent events, the probability of the union is the probability of A plus the probability of B, but now we can subtract the product of the two probabilities, right? So that's the formula we're going to have if we have the union of two independent events. Let's consider this example. We've got the event of tossing a fair die and flipping a fair coin. Okay, so there we have, let's say the event A is getting a 5, tossing a die, right? And what would the outcome be then? So the probability of event A, there's only one way we can get a 5, so that's 1 over 6. And event B, getting a head, flipping a coin, and getting ahead, there's only one way to get ahead, so that's 1 out of 2, so that's a 0,5. Now if you look at that here, flipping the coin is not affected with, if you toss a 5, that tossing of the 5 is not going to affect the flipping of the coin there. So those two events there are independent. So A and B, there's no overlap between the two. The one does not affect the other one. So therefore we can say that event A and event B, tossing a fair die and flipping a fair coin, are independent events, right? You can see there, probability of A times the probability of B. If I want to calculate that probability, I find the product. So it's 1 over 6 times 1 over 2, and 1 over 6 times 1 over 2 is going to be 1 over 12, right? So if they are independent events, I can just find the product of their two probabilities. Now let's have another example illustrating independent events. Here we have 3 balls, red, yellow and blue. You can see red, yellow and blue are placed in a box. A ball is randomly drawn from the box. Its color is recorded and it's replaced. So you draw the ball and you put it back again there. A second ball is drawn and the color is recorded. Determine the probability of drawing a red ball and then a blue ball. See, there's the and coming in. So let's look at this one here. So event A is drawing a red ball. Okay, so if we draw a red ball, see there we're taking out a red ball, and what's the probability of drawing a red ball? Right, there's only one red ball, so its probability is 1 over 3. But it says replacement, so in other words we must put the ball back again. Then event B, we want to draw a blue ball. So if we draw a blue ball, that is 1 blue ball out of the 3, so the probability of drawing a blue ball is 1 over 3, right? So you see, drawing a blue ball was not affected by drawing a red ball because I replaced it there. So those two events are independent. So probability of a red and a blue ball, because they are independent events, is the probability of drawing a red times the probability of drawing a blue. In this case it's 1 over 3 times 1 over 3, and that gives us a product there of 1 over 9. Okay, because they are independent events and their replacement. So in other words, your sample space didn't change there. Let's look at another example here. Here we have a fair coin that is being tossed, and then a spinner is spinned with the 5 numbers 1, 2, 3, 4, 5, and we want to determine the probability of getting a head and an even number. Now you can see those two events are independent. You know, the spinner is not, doesn't matter whether the coin lands head or tails, it doesn't affect the spinner, so they are independent events. So the probability of getting a head and an even number is the probability of getting heads times the probability of getting an even number. What is the probability of getting heads? 1 over 2. Probability, how many even numbers are there? It's only 2 and 4. So that's a probability of 2 out of 5. Therefore, the probability of getting heads and an even number is 1 over 5. Now let's consider the concept of dependent events. The outcome of the second event is affected. Here it is affected by the outcome of the first event. So in other words, the product rule of dependent events is going to be slightly modified now. Probability of A and B is the probability of A, the first event, times the probability of B, but after the first event has occurred. You see, there's a little difference there. Probability of B after the A, because that there's something at the first event, the outcome of the second event is affected by the outcome of the first event. So we're going to just show you what we mean by that there. To illustrate this, we take the same example, but we're making just a slight change here. We have the 3 balls, red, yellow, and blue, and a ball is randomly drawn from the box, but here we have it's not replaced, right? So once you take the ball out, you don't put it back again. That's where the difference is coming. So now the outcome of drawing the blue ball is going to be affected by the event A having taken place, and we say that it's not being replaced there. Now let's look at this solution here. There's our box with the red and the yellow and the blue ball. So event A is drawing a red ball. So if I draw a red ball, there's the red ball there. And the probability of drawing a red ball from the 3 is the probability of getting a red is 1 over 3. But now we had the restriction no replacement. So that ball is not being placed back. So I'm left with 2. So what's the probability of drawing a blue ball? Probability of drawing a blue ball, that is going to be 1. There's 1 blue ball and there are 2, so the probability of a blue ball is 1 over 2. So you can see there's a difference, right? Drawing the blue ball has now been affected by the first event, because the first event I removed the ball but I did not replace it. So in this case here we've got dependent events. And how do we do that? Probability of red times the probability of blue after red has occurred. Okay, so what's the probability of red? 1 over 3. But drawing the blue after the red, there's a change now. It's 1 over 2, not 1 over 3. So that is going to be 1 over 6. Now let's consider this example here. We have 2 different events A and B such that the probability of A is 0,5, probability of B is 0,4, and probability of A or B is 0,6, right? Now we are asked to determine whether A and B are independent events, and we have to justify our answer. So if they're going to be independent, we have to show that the probability of the intersection is going to be the product of their probabilities of the 2 events. So let's see there, we take our addition rule and we are given some values, so we can do the substitution. Probability of A or B, that's given as 0,6. Probability of A is 0,5. Probability of B is 0,4. And now we can calculate the probability of A and B. If we calculate that, it's 0,5 plus 0,4 subtracting 0,6, and that gives us 0,3. Okay. We also have to calculate we calculated this portion. Now we need to calculate the product of their probabilities. Probability of A, that is given as 0,5 times 0,4, and then if I do that product, that gives me 0,2. And we now notice that 0,2 is not the same as 0,3. In other words, we see the probability of the intersection is not equal to the product of their 2 probabilities, right? That's what we have there. So in other words, it's not independent. Therefore, we'll say A and B are dependent events. In this unit, I'm going to do applications using contingency tables. Wherever this icon appears, pause the video, try the example, and then start play again, and then you can compare your solution to the one that I have provided. Now we're going to look at another way in which sample spaces can be represented, and this is known as a contingency table. Now a contingency table is a table summary. It's a summary in a table form of large data set of categorical data of 2 variables with a number of categories. So it's data, 2 variable data, but each of the variables, they have categories, subcategories for each variable there. Okay. So we also refer to a contingency table as a two-way table, and we'll illustrate that to you. But the main purpose is, if you have large data sets, you can summarize the data in a contingency table. So let's consider this example here. We have data regarding gender and home language, right? So gender, there we have our table, and you can see gender is the one variable and home language is the other variable. And then we have 2 categories for gender, male or female. And then for home language, it's either English, Afrikaans, and isiXhosa, right? So we represent male with the M and the F, and there we have got E, A, and X there. Now you see there's the data. So we now just have to complete this table. So we have to see, if I have to look at male, how many males are there and how do we find that? We have to find the total there, right? How many females are there? We have to find the total. How many people take English? So we have to complete this table by getting the total. So let's get the total for English, 35, total for Afrikaans, 25, total for isiXhosa is 40. And then we have to find the total for male. There are 45 males, and the total for females, that's 55. And then we can cross-check. If I add this total here, right, it must give me exactly the same if I find the total horizontally. And if we do check that, we see the total there is 100, right? I've just used some cosmetic numbers to make the calculations a little bit easier. So 35 plus 25 plus 40, that gives me 100. 45 plus 55 is 100. So there I've completed my table. As you can see, there were 2 variables, and each variable had subcategories. So for gender, I had male, female, and for home language, I had English, Afrikaans, and isiXhosa, right? So let's use that contingency table now, and then we can get the probability of randomly selecting a male, right? So I want to select a male randomly. So let's look at the males there. There's the males, and how many males are there? That's correct, 45. So, and how many people are there all together? In the survey there were 100, so the probability of getting a male is 45 over 100, right? 45 over 100 is, in this case, nicely 45%. I can simplify that as 45%. Let's look at another example. The probability of randomly selecting a person with English as a home language, right? So English, this is just a person with English, so I have to follow the English. And how many people have English as a home language? That's 35. So the probability there is 35 over 100, and 35 over 100 is just 35%, right? Now let's continue. We use the same contingency table, a completed contingency table, and let's look at this example now. We want the probability of randomly selecting a female whose home language is Afrikaans. So it's female and the language is Afrikaans. So we have to look at female. There's female and Afrikaans, and you see female and Afrikaans, they overlap. So there are actually 10 people with female and his home language is Afrikaans. So then the probability of that is going to be 10 over 100, and 10 over 100 is just 10%. Next, we want to find the randomly selecting a male whose home language is not isiXhosa, right? So we want the males, but we want to see those whose home language is not isiXhosa. So we don't want these people. So it's all the males, and then we don't want isiXhosa, so it's the English and Afrikaans. And we see there it's the 20 and the 25. So how many males whose home language is not isiXhosa? That is 20 plus 15. So the probability of getting that male and whose language is not isiXhosa, so that gives me 20 plus 15, and that gives me 35 over 100, which is 35%. Now let's consider another example where the contingency table can be useful in probability questions. Let's take the same example of gender and home language. There we've got our completed contingency table. Let's look at the question. Determine whether gender and home language are independent events, right? So what I do is I can take one of the categories of gender, and one of the categories of home language. Let's choose male and Afrikaans. So probability of male and Afrikaans. There's male and Afrikaans. See, so there are 15 of them being Afrikaans, males whose home language is Afrikaans. So that probability there is 15 over 100, which is 15%. Right? Next, we want to find the individual probabilities. Probability of male times probability of Afrikaans. Probability of male, if you just go back to that again, we see there are 45. So the probability there is 45. Probability of Afrikaans, there's the Afrikaans, and there are 25. So that's 25 over 100. Doing a little bit of calculation there, we get 11.25%. So now we notice that that 15% and that 11.25% is not the same. So therefore we can deduce here that the probability of M and A is not equal to the probability of M times the probability of A. In other words, the product for independent event, the rule doesn't apply here. So therefore they are not independent events. In this unit, we're going to look at some applications using tree diagrams. Wherever this icon appears, pause the video, try the example, then you start playback again, and then you can compare your solution to the one that I have provided. Now let's look at another representation that can assist us with calculating probabilities, right? Tree diagrams. They are used to provide a visual representation in an organized way of a sample space and to calculate the resulting probabilities, right? The outcomes of events can be found at the end of each branch there. So the purpose there, it gives us a visual representation in an organized way of a sample space and to calculate the relevant probabilities there. To illustrate the use of tree diagrams, let's consider an example. We've got a packet containing some paper clips. We have 2 red, 3 green and 5 blue paper clips, right? One paper clip is randomly selected from the packet, the color recorded and then replaced. The emphasis here is we put it back in the packet. Another paper clip is then randomly selected from the packet and the color is recorded, and we can continue that way, right? So we've got 3 questions here. We'll show you how can we represent this information in an organized way as a tree diagram. Then we're going to calculate the 2 probability questions that we're going to do that. Now let's construct the tree diagram. Let's look at the given information. We've got 2 red, 3 green and 5 blue, and here we've noted that we replace, once we take out a paper clip, we put it back. So let's start. Let's have the first pick. So if my first pick, it can either be a red paper clip, or it can be a green one, or it can be a blue one. How many red paper clips are there? 2, and then we have a total of 10. So I'm just using some nice numbers here. 2 out of 10, then I get 3 over 10, and then I get 5 over 10. Right? Now I can have my second, and I put it back. So once I take out a paper clip, I replace it again. So in my second pick, I can again choose either a red, a green or a blue, and exactly the same. After I've chosen maybe a green, I can take a red, a green and a blue. After I've taken possibly a blue, I can take a red, a green and a blue. Because I've replaced, my sample space size has not changed there, so I still have exactly the same probability values: 2 over 10, 3 over 10 and 5 over 10, and that's exactly the same there. Okay, now let's list the outcomes and let's list the probability. So there's the outcome 3, 3, and what will RR, and we just follow the colors, so that's 2 over 10 times, and the probability would be 2 over 10 times 2 over 10, because they are independent events here. So 2 over 10 times 2 over 10 gives me 4 over 100, and 4 over 100 simplified is 1 over 25, right? The next one is going to be a red followed by a green, and that will be 2 over 10 times 3 over 10. I've color coded to make it easier. That gives me 6 over 100, and we simplify that, that's 3 over 50. The same way, I get a red followed by a blue, so that's 2 over 10 times 5 over 10. That's 10 over 100, and that's 1 over 10. And I can do the same there. That's a green followed by a red, and then a green followed by a green, and a green followed by a blue. So I can get all my outcomes there. There's my outcomes. I can calculate the probabilities. There's the probabilities for green and red and green and green and green and blue. Simplify that. Those are the values I get there. In exactly the same way, I can calculate the probability. That's 5. I can just follow the colors. 5 over 10 times 2 over 10. Then 5 over 10 times 3 over 10. And 5 over 10 times 5 over 10. Calculating that. And then, right? Quick bit of arithmetic. If you add up 1 over 5 plus 2 over 5 plus 1 over 10, etc., up to 1 over 4, the sum of these probabilities will be exactly 1. And just double check that, give you a chance to try it. Can you see it's exactly 1? So there I've completed my tree diagram. As you can see, it's a nice organized way. You know, you can see that's your first pick and your second pick. It even shows your outcomes, and you can actually see the probabilities there, right? I've just used the colors to make it easier for you to follow what's happening. So there I've completed my tree diagram. So that's the first part of my question, drawing the tree diagram. Now let's see how we can use our tree diagram. So there I've got our completed tree diagram. I've just taken some of the other calculations out, so just make it a little bit more simpler there to use. We want the probability of selecting first a red followed by a blue, right? So I've got red followed by a blue, and this is I'm going to use my product rule because they are independent events. So A will be red and B will be blue. So let's see probability of a red then a blue. So I follow a red and then blue. Can you see that? I go along that way and along that way. And there's my outcome, red, blue. And what is that there? That is going to be 2 over 10 times 5 over 10. Probability of red times probability of blue, 2 over 10 times 5 over 10. It gives me 10 over 100, which is 1 over 10, which obviously is 10%. Right, so there I've calculated that one. Now let's look at another question here where we can use this tree diagram. Determine the probability of randomly selecting a green and a blue. So I have to follow where do I have a green paperclip and a blue paperclip. So let's do that. Green and blue. Let's follow that. You see there's green and there's blue. Okay, that's a green and a blue. Where else do you see a green and a blue? There's a blue and then a green. You see there's another one. So there are 2 here. And because of the and, I will have the probability of green and blue. And then I'll add to that the probability of blue and green. Right? So that's 3 over 10 plus. And blue and green is another 3 over 20. And that gives me a total of 3 over 10. Okay? That is 6 over 20, and 6 over 20 is the same as 3 over 10. So there, that's the probability of getting a green and a blue. You see how easy it is to use the tree diagram to get our probabilities there. Now, let's take the same problem, but we're going to modify it slightly. Okay? You can see we still have our 2 red and 3 green and 5 blue paper clips, but now we say not replaced. You see the previous one we had replaced, so let's see what the tree diagram looks like if we say not replaced. So there we have 2 red, 3 green and 5 blue, and we're noting that it says no replacement. So let's start off there. Then we want to get our tree diagram. So again there, our first pick, we can pick a red, a green, or a blue. Okay, and again there, because we have 2 red, it's going to be 2 over 10. So first pick 3 over 10, and the blue is going to be 5 over 10. But now we say there's no replacement. So once you take out a red, you started off with 10 paper clips. Now you have 1 less paper clip. Right, so my second pick, I'm also going to get red, green and blue. And I'm also going to get red, green and blue for my second pick, and red, green and blue. But let's see what the probabilities would be now. Because my sample space is now changed, you see this is now not independent. The second pick depends on what happens on the first pick. So if I had 2 red and I already took out one of the reds, I have, how many reds do I have left? Now I only have 1 red left. But I haven't replaced the red, so I now have 1 over 9. I haven't taken a green, so I still have my 3 greens, but I only have 9, so that's 3 over 9. Okay, I haven't taken any blue, so that's 5, but now it's 5 over 9. as you can see, with no replacement, that denominator of 10 now becomes a denominator of 9. You can quickly do with a little bit of maths here. 1 plus 3 plus 5, it still gives me 9 over 9, right? So just be careful here. Here I've got 3 over 10. So now I'm going to have 9 paper clips left. I haven't taken a red, so I still have 2 over 9. I've taken a green, so instead of having 3 greens, I now only have 2 to choose from. I haven't taken a blue, so that's still 5 over 9. The same way here, as you can see, that's the denominator of 10. There I've got a denominator of 9. I haven't taken a red yet, so it's 2 over 9. I haven't taken a green, so that's 3 over 9. But I've taken a blue, so I don't have 5 blues to choose from now. I have 4, so that's 4 over 9. You can see the sum of the probabilities on these 3 branches is 1, the sum there is 1, and the sum there is 1. Okay, I can write down the outcomes again. So the outcomes there is exactly red and red and red and green, right? I can calculate, and you see now I get 2 over 10 times 1 over 9, so that gives you 1 over 45. And the same red and green, it's going to be, you can just follow the colors there. That's 2 over 10 times 3 over 9, which gives me 1 over 15. Red and blue is 2 over 10 times 5 over 9, which gives you 1 over 9. Okay, and then if I take green and red and green and green and green and blue, and then blue and red and blue and green and then blue and blue, and if I calculate the probabilities, that's what I get there. I calculate the probabilities, I get that there. And if you add up all these fractions, you can just double check, you'll get exactly 1. Okay, so there's the tree diagram with no replacement. Note there the sample space size is 10, there the sample space size here is 9. Now let's consider an example here. We want to determine probability of a blue, then a blue. So that's dependent events because there's no replacement, and therefore it will be the probability of the first event times the probability of the second event after the first has happened. So then it's blue, probability of blue times the probability of blue after blue, and there's the probability of getting a blue, that's 5 over 10, and then the probability of getting a blue again, but now it was no replacement, so that is times 4 over 9, and that gives us the 5 over 10 times 4 over 9 gives me 2 over 9. So that is blue, then blue, and this is one with no replacement. In this unit, I would look at applications using Venn diagrams. Wherever this icon appears, pause the video, try the example, then you can start play again, and then you can compare your solution to the one that I have provided. Now let's try to understand our Venn diagram, right? There we have the Venn diagram, and we have the number of outcomes as represented by E, A, X, D, H, B, and K, and M, and those are E, that's A, the region A, so that's that A part. H would be that part there. Okay, so if I look at C, I will see C consists of the E, A, the X, and the B. If I look at F, F consists of the K, the D, the X, and the B. Same way, V consists of the A, the X, the D, and the H. Now if we say only C, right? So if I take only C, if I look at C, right, there's C. Only C, you know, C consists of the E, the A, the B, and the X. But B is not only C, B is part of F. X is part of F as well as V. And A is part of A. So I have to remove those parts. I remove the parts from V, and I remove the parts from F. So that region that's highlighted there, that is the only C. And that one consists only of E. So that one will be E. Now if I take the next one, only V, so if I look at V, and you see there are parts that are not only V, that's the A, the X, and the D belongs to others as well, belongs to chicken and fish, so I have to remove the fish part, and I remove the chicken part, and that leaves me with the only V. In this case it's represented by the region H, so only V is H. Similarly, if I want only F, then only F here would be there's the F, but I see F there consists of the B, the X, the D, and the K, but B, X, and D it's not only F, it belongs off to others as well. So I have to remove this chicken part and I have to remove the vegetable part. So the only F is then represented by that region K. So only F is K. Now let's go back to our three events again. Here we want the concept of not C, right? Or as we say there, the complement of C, or C prime, the complement of C. So not C. So if I say not C, I don't want the elements of C, right? In other words, that's what I don't want. And what is left there? So I don't want that, so I must take the C away. And what is left now? You see what is left? That's correct. There are 4 there. That is equal to the M plus the K plus the D plus the H there. Remember, this stands for the number of outcomes there. So it's M outcomes, K outcomes, D outcomes, and H outcomes. So I find the sum there. Let's go back again. If I want not V, so that means it's not the V. So I don't want those elements. So take those elements away. And now you can just write down what is left. So not V would be those 4 parts there. It's going to be the E, the B, the K, and the M. And we find the sum, so that gives us the sum M plus E plus B plus K. Similarly, if we say not F, so I don't want the F, so I must remove the F. I don't want the F, right? So what is left there? M, E, A, and H. So that is M plus E plus A plus H. And now if we say not C or V or F, right? Not C or V or F, so I want not the C, right? And the V or the F, so I don't want those elements. And what is the only thing that's left? That's correct, it's only M that is left there. Okay, so that answer there would be, see, it's only the M that's left. So not C or V or F, that is equal to the M there. Let's go a little bit further now. Now we want to have the and, C and V, right? Before we show that to you, can you see the and part? C and V. Right? That is the C, that is the C and the V, the A and the X part. That's the only and, that's the and part there. So the and part there would be X plus A. Okay, let's bring everything back again. So now I want V and F. Can you see the V and the F? There's V and F. So what would be the and, or the intersection? That's the intersection, that portion that's highlighted there in white, and that's the X plus the D. Similarly, if I want C and F, right, can you see the C and the F? That's correct. That is the C and the F part. So it's that part there, which is the X plus the B. So that's the X. And now if we want C and F and V, right, all 3 of them, right, the intersection of all of them, that's that portion there, that belongs to all 3 of them, and that is only the X there. Let's take our diagram back again there, 3 events. Now we want or, C or V, or C union V. C or V, so I want the C or the V, so that is the C or the V. Can you see? That's the C or the V. Okay, and it's those 6 parts there. We have, there's the C or the V, so that's going to be E plus A plus X plus B plus H plus D. Okay, let's bring everything back again. C or F, you try this now. Can you see that? That's correct. That's the C or the F, right? Isn't it? Right? And that there would be those 6 parts. There's the C or the F, and that will be E plus A plus X plus B plus K plus D. Now V or F, let's see, where's V or F? V or F would be those 2 there. So those are those 6 parts. There's the V or the F, and it's K plus B plus X plus D plus H plus A. And now C or V or F, what does that represent? Give you a chance. That's what it is, right? But it has to take the M out. The M is not part of it. So it's those 7 there. So it's going to be E plus A plus B plus X plus D plus H plus K. Now let's do an example on a Venn diagram of 3 events. Right here we have a case with 103 learners, and it's their food preferences here. That's chicken, vegetables, and fish. And here we have some information about that. So the first question there would be, we'd like to represent that in a Venn diagram. Then we have to calculate the missing value, and then there are some probability questions there. We're going to do each one separately. So let's go to the next slide. Draw a Venn diagram to represent the information. So that is what I need. So I just have my blank Venn diagram there. C stands for chicken, V for vegetables, and F for fish. Okay, let's see what's the first information that's given. 103 learners, food preferences. What's that 103? That is the total number of outcomes in the sample space, 103. Right, so I put the 103 next to the X. Then next we say that 2 eat only chicken. Can you see the only chicken part? That's correct. That part there, that's the only chicken, right? So this part here, that's the only chicken. Then the next one here, we want 3 eat only fish. Where's only fish? That portion there is only fish. So I can insert the 3 there. Then the next one, 5 eat only vegetables. Only vegetables, so the 5 would go there. Right, so that's that one. The next part there, 2 do not eat chicken, fish, and or vegetables. You know where that is? They don't eat chicken, fish, or vegetables, and you just have to put it outside. There's the 2. Now let's see the next one here. 21 don't eat fish. Right, so if they don't eat fish, in other words, it's not these people. So it's this one, and this one. So it's 2, this part, and this part here. Okay, so all together that should be 21. So I can find the missing part there. And how do we do that? That's because that's the part we want, right? So it's 21 minus 2 minus 5 minus 2, and that gives us a 12, right? So 21 don't eat fish helps us to get that particular portion here. Now next they say X is the number who eat chicken, fish, and vegetables. Where's the and part? Chicken, fish, and vegetables. That's correct. That's the part right in the middle. That's the X. Okay. Then next, 75 learners eat vegetables and fish. Where's vegetables and fish? There's vegetables and there's fish. So this whole portion here, that should be 75. Not 75 here, but 75 between them. So to get this part here, it is 75. That's correct. 75 minus X. Okay. Similarly, 66 eat chicken and fish. There's chicken and there's fish. So the 66 is here. There's the 66. The 66 is there. So this portion here where the pointer is, that is 66 minus X. Okay. So there we've represented all the sections there. Now, the next question is, now we want to calculate that value of this X here. Okay. Now what do we know there? The sample space consists of 103, right? So the size of the sample space there is 103. So all of this together should be 103. So 2 plus 12 plus 5 plus 6 minus X plus 75 minus X plus 3 plus 2 should be equal to 103. So I set up that equation there, and this should be quite an easy linear equation to solve. And solving that, we end up with X equal to 62. So this is 62, and once we have that, we can say 66 minus 62 and 75 minus 62. That will make it possible. Now let's look at the probability questions here, and it's important that we read the questions carefully. We have to determine the probability of eating only chicken and fish. So if I look at chicken and fish, that's the chicken and fish, right? So that's the 4 and the 62. But they say no vegetables, so I must take the vegetable part away. So that only leaves us with that 4. So only chicken and fish, but no vegetables. That is 4 over 103. Next question. Probability of eating any 2 of the food choices. Any 2. So it must be 2 of the food choices. If I am there, I only have 1 choice. Here I have two choices. There I have, because that is chicken, and there's another two choices, and there's another two choices, right? So it's the 4 and the 12 and the 13, right? Only two. I cannot use this here because that's 3 food choices. I said eat any two of the food choices. So any two of the food choices is 4 plus 12 plus 13. So that's the 4 plus the 12 plus the 13, and everything we divide by 103. So that gives us a total of 29 over 103. Now let's look at the third question here. Determine the probability of eating chicken or fish. Chicken or fish. Chicken or fish would be that there. Those are the 6, the 2, the 12, the 4, the 62, the 13, and the 3. And we find the sum of that. So chicken is 2 plus 4 plus 12 plus 62 plus 13 plus 3. Get that total is going to be 96. And then the last one, probability of not eating fish and not eating vegetables. So be careful there. Not eating fish. So in other words, we exclude these people here. Okay. And not eating vegetables, we exclude that there. So we've excluded this and we excluded that. So we only left with the 2 and the 2. So that answer is 2 plus 2 over 103. So that's 4 over 103, right? If we had a question here, the probability of not eating fish and vegetables, right? So if I say fish and vegetables would be these people here. Okay, that would be fish and vegetables. And not eating that would be the others that I would have there. 5, the 12, the 2, the 4, the 3, and the 2. Now let's come to the most important part here, and this is the exercise worksheet for you now to practice. I've taken questions from previous external question papers and I've referenced them. Some of the questions I've slightly adapted. This is a question from the exemplar 2014. First question here has to do with mutually exclusive, and here's a question here where you have to use a tree diagram with some probability applications. In the second question here, this is from February 2015. This here is a question where you have to use apply Venn diagrams, right? So this is a Venn diagram question there. And question 3, this is a question also where you have to use a Venn diagram with slightly different information here. And question number 4, this is a question where we have to apply the concepts of dependence, in this case independence. I hope this video helped you to understand the probability concepts, and please also view other videos on grade 12 mathematics topics, and please once again subscribe to my channel, Maths with Armien. Until next time.